Welcome back to another class of Math 365 PDE. So I want to briefly review what we've done so far in the course, if you kind of track the progression, right? So we started out introducing like what are PDEs. We introduced kind of like 4 fundamental PDEs: transport equation, which solved by the method of characteristics, wave equation, which we've been talking about extensively, the heat or diffusion equation, and also Laplace's equation. And we first solved the transport equation with a method of characteristics, even in higher dimensions. We then used that method of characteristics or coordinate change to solve the wave equation with D'Alembert's formula. That was on the entire real line. We then leveraged that formula to solve wave equation on a finite interval by, if you had Dirichlet boundary values, take the odd extension, use D'Alembert's solution, and then restrict back. If you had like from the exercises, if you had like Norman boundary conditions, you could take an even extension, use D'Alembert, solve it, and get it back. We also then introduced this idea of like a product solution or separation of variables so that we could find the fundamental frequencies of the string. So these are these particular solutions for a vibrating string at a certain frequency. Then we moved on into dimension 2 to find the vibrational frequencies of the vibrating drumhead. So once again, these are particular solutions to like the problem of a vibrating membrane with like circular membrane. And in order to do that, we even had to introduce this Helmholtz equation and confront like the eigenvalue problem for the Laplacian, which led us to Bessel's function. But what I was saying at the end of class is you get this reasonable question where you've got, all these individual solutions that are based on this frequency or that frequency. Could you add them up in such a way as to fully solve the problem, in the same way that D'Alembert fully solves the problem given initial conditions. And I could kind of explain that in the context of solving the 2D wave equation, but actually that has so much writing and so many constants. I think it's better to explain it back in a one-dimensional problem. And also this technique is equally valid for a heat equation and wave equation. And so, in fact, we haven't talked about the heat equation very much this semester, so I think I'll go ahead and talk about it now and try to just illustrate this principle to you. So what I really want to do is I want to solve this following boundary value problem for the heat equation, which you'll remember heat equation is like one time derivative equals diffusion constant times 2 space derivatives. And you're wanting to do this on some rod of length L. And you might hold the ends of the rod, at fixed temperatures. For simplicity, so for this time, we'll take U T0 equals U TL equals 0. So holding the endpoints of the rod fixed at 0 degrees. And then we also have this initial temperature distribution. And so necessarily f of 0 equals 0 and f of L equals 0, but you could have any temperature distribution that you want. The regularity of f is to be specified later, whether or not we need this to be like a C2 function or whatever. So this is the problem that I'd like to solve fully. And I'd like to do separation of variables in order to do it. And So yeah, let's give it a try. So let's take u equals v times phi, with v a function of t and phi a function of x. And if you just sort of plug this in to the equation, you'll end up with vt times phi. So this first part we're quite familiar with in the context of the wave equation, but here we are trying to solve a specific problem. I'll go through all the details. And so we get k times v times phi double prime, the partials with respect to x turning into pure derivatives on phi, partial with respect to t turning into a derivative on v. And what do we do? So, I mean, once again, you could add in this caveat that u should be bigger than 0 on whatever region you're hoping to make this technique work on, because you want to divide both sides by u. Actually, I'll maybe divide both sides by k times u to end up with v prime over kv equals phi double prime over phi. And then this is what we've been calling minus lambda. And we'll certainly continue to do that. Although lambda no longer, it's no longer characterizing a vibrational frequency. You can, as we go forward, you can try to think like whether or not lambda has like a physical interpretation that you kind of like for this problem. And so like before, this leads us into two equations. So it leads us into v prime equals minus lambda times k times v. And it leads us into phi double prime equals minus lambda times phi. And there's also initial conditions, right? So we can plug in our initial conditions and let's see what happens. So first, I'll handle this. So ut0 is saying, yeah, it's saying what? Phi of 0 times vt equals vt phi of L equals 0, and assuming that function v is not identically 0, which is like a reasonable assumption, right? We're not looking for the 0 solution here. Looking for non-zero solutions. You could divide out both sides, and you could end up with phi of 0 equals phi of L equals 0. So you have this nice spatial boundary condition. Of course, this equation we're quite familiar with. We've seen it before with the wave equation already. And this one is a little bit new, but also no problem. So you solve this with ODE, with either the ODE version of separation of variables, or with Euler's trick of the integrating factor, or just sort of stare at it for a while and say, this looks like v sub t has to be something like a constant times e to the minus lambda kt. So such functions come with the initial condition that v of 0 equals a. But actually, hold up a second, because don't we have another initial condition? Don't we have u0x equals f of x? So let's write that down. And if you do that, you get what? V of 0 phi of x equals f of x. And so either you kind of put this bizarre restriction that v of 0 must be 0 to make this equation vacuous, or you end up with phi is equal to f, which is not going to work, because you can't just F is completely arbitrary. You can't say that an arbitrary function will automatically solve this equation. So this initial condition is completely incompatible with this setup, right? Well, I'm just saying, like, if you write U, so the student question was what? I'm just saying, if you write U equals V times phi, and like this initial condition is kind of nice to you, in that it gives you these nice boundary conditions, but this initial condition, just plugging in to U0x is now V of 0 times phi of x. Like if you're saying that's equal to f of x, isn't that like saying that V of 0 has to be 0, which is like imposing a condition on you that you don't want? Or isn't it saying that phi of x would have to be f of x?
But I thought we had arrived on the conclusion that V of 0 was 8 now.
Well, in order for, so generally speaking, the solution to this equation is that, and V of 0 will be some constant, right? So sure, if A is non-zero, then phi of x is equal to f of x, certainly. Which is then impossible, because just choose f of x to be x, right? Or then it doesn't solve this equation. So you therefore have not solved the heat equation.
Okay, because f is any arbitrary.
Right. I mean, f will have some conditions later, but those conditions are like it has to be continuous, you know, or not like f has to be sine theta or something like that. Yeah, so definitely it's not true that you can just separate the variables and like out comes an answer. But what we can do is we can recognize that the particular solution we find, even though the particular solution we find for separation of variables will not solve this initial value problem, perhaps it will be true that we can add up a number of our individual solutions that came from separation of variables. And that sum will then allow us to handle this initial condition. So to be clear, the hard part about this problem is not solving these two equations. It's how to make the initial condition work with the equation. Why didn't that appear when we were talking about frequency harmonics? Because we were not talking about general initial condition. We were talking about finding just any particular solution that vibrated at whatever harmonic. And those solutions happen to be products. But let's sort of set this aside for now. Let's put this in a box. So it can't affect us. We'll put it.
Is that box thing the new condition that prevents us from using this method?
Well, this is the condition that made separation of variables not useful, right? But let's not give up on separation of variables just yet. Let's just sort of set that aside and maybe return to it later. And so here's the story of how you can maybe resolve this. So here's the story. With a really clever argument, you can get around this sometimes, but not all the times. And like everything else in PDE, you've got different methods that kind of work here, but they don't work there, you know? So we're illustrating one method that's quite cool for how you might solve this. Okay, but let us get into it. Let's look back at this solution. So we know that whether you can solve this or not depends upon whether or not lambda is is 0 or negative or positive. I mean, certainly you can solve this in all three cases, but the character of the solution will be different. If lambda is equal to 0, then phi of x has to be ax plus b, right? With maybe a different constant than here. Hope you don't mind me kind of reusing a and b for generic constants. And look at your boundary values. So plug in 0 for x, giving you b equals 0. And now plug in L into phi of x, giving you a equals 0. So if eigenvalue lambda were equal to 0, then there's no solution to this problem, at least not one that's non-zero, which is what we're interested in. So just like in the vibrating drum case, but we end up excluding this eigenvalue. The boundary value is saying that your endpoints are kept at fixed temperatures. So heat is transferring from the boundary points into the rod. And so the steady state solution for this is the 0 function, because whatever your initial temperature profile is, it'll be, it'll eventually settle down to nothing. Unless, well, I guess under this model, I should say it doesn't settle down to 0, it settles down to a constant, because if you're not losing energy, then maybe it can't go to 0, but it'll go to a constant or something.
What is the physical meaning of lambda in this case?
Yeah, that's my question for you. That was my question for you, that you could think about at the beginning of class. Yeah. But I think it's an interesting question, because lambda had a clear meaning for like vibrational frequency for wave equation. But I'll ask you to sort of ponder that outside of class. So for lambda less than 0, for lambda less than 0, so what do we get? I think we get solutions of the form constant times e to the root minus lambda t plus constant times e to the minus root minus lambda t. Remember this business? You solve the characteristic polynomial, and then the roots give you the independent solutions. You take linear combinations of them to get your answer. X, thank you, yeah. Getting back into ODE mode too much. And like once again, you can start like plugging in your boundary conditions, right? So if you start looking at phi of 0, so phi of 0 equals 0, it's also equal to a plus b, so a equals negative b, and then look at phi of L, which is now a times e to the root lambda L plus b minus root negative lambda times L, which is also equal to 0. And so now you can, I'd like to argue that A and B are both 0. Would any of you like to help me out? How would you argue that? I'm going to take a drink of water outside, but then I'll come back and hear your answer. Yeah, so the question is, how do you try to show that A and B have to be 0?
Well, the exponential values are going to be, whatever they are going to be opposites.
Well, these exponential values are real numbers, right? They will be reciprocals.
Fair.
Are they real numbers?
Yeah.
Because you're in the case where lambda's negative.
Well, then, unless L is 0, we're guaranteed to require A and B to be different magnitudes.
Yeah, that's right. So A and B are two constants. A is equal to negative B. So if you make that substitution into this equation, what do you get? Like B, so negative B, and then factor it out, and then you're like e to the minus root minus lambda times L, and then maybe minus e to the root minus lambda times L. And so this is sort of like a contradiction proof. If A and B are not both 0, then you can divide through. And you're left with this assertion, which is false.
Unless L is 0.
Yeah, but it's not.
Right.
You're not doing an equation on the, yeah, unless you had like a degenerate thing. But yeah, so that leaves us with lambda could be bigger than 0, and in this case, you get these two independent complex solutions, or you can write, or you could write like A times cosine root lambda x plus B times sine root lambda times x. And we had this argument, didn't we, that root lambda had to be a particular thing, right? So you use the boundary values. So first of all, knowing that phi of 0 equals 0 immediately tells you something about these coefficients. So which coefficient is 0? Knowing that that's true. Yeah, A has to be 0. And secondly, 0 equals phi of L is now equal to B times sine root lambda times x. Now, clearly we don't want to choose B to be 0 here. we want to find a condition on lambda to make this, right, we want to find a condition, thank you. We want to find a condition on lambda so that this equation will be true. And of course, we've already done that, and we found that lambda had to be n squared times pi squared over L squared. So we actually get the same condition on lambda that we got in the vibrating string. So you're getting now these solutions, phi sub n of x equal to, I'll call it now bn because they're indexed now by the integers. So this is going to be b sub n times sine of n pi over L times x, and this also has ramifications for your v of t, because now you've really got a function u sub n equals v sub n times phi sub n, right? You've got one for each n. These lambdas are now cleanly indexed by the integers, and so v sub n is just going to be maybe like some constant times e to the minus n squared pi squared over L squared times K times T. And so you get these solutions, U sub n. And there's two arbitrary constants. I really only need one constant, you know, when I multiply them together. So I'll keep that going. I'll just call it B sub n times e to the minus n squared pi squared over L squared times K times T times sine of n pi x over L. So these are your product solutions for the diffusion equation. There's one for each n. So any question or comments on that?
Complete solution be the sum of all those?
Yeah, that's, so the question is like, would the complete solution be kind of like the sum of all of those? And yeah, that's exactly the idea. There is a little bit of an issue because n ranges throughout all the integers, but sine is an odd function. So actually, I mean, when n is equal to 0, you just get 0, so just like throw that out. And when n is negative, those are just the negatives of the solutions when n is positive. So actually, I think that our real range for n is that n is bigger than or equal to 1. And now this gives us a collection of what you call linearly independent solutions in a certain sense. Like you take the Wronskian of any two of them or something and be non-zero. And so, yeah, it's quite a natural idea, and this was Fourier's idea, which was to say, look, like we had a very specific problem we wanted to solve, which is this problem with initial temperature distribution. We ended up with these product solutions, one for each n. Could it be true that UTX might be equal to the sum, well, of the UNs? So this is like expanding your idea from linear algebra, if you like. In linear algebra, you take a vector and hope that it's a sum of like a coefficient times basis vector 1 plus coefficient times basis vector 2, so on and so forth. Here you've got a function and you're hoping that it's a sum of like this sort of countable collection of solutions. And of course, this has to actually converge. So you have to choose coefficients to make this thing actually converge. So like that's an issue, but say that it does, say that you can differentiate out of the integral sign. Can we make this work at all? I'll remind you, infinite sum is a limit of partial sums. So if I take like n goes from 1 to capital N, this is the definition of Sn for partial sum. And the definition of infinite series is it's a limit of the corresponding sequence of partial sums. And then the definition of limit of sequence, I'm not going to go through right now, but at least that kind of brings into your mind like a baseline of familiarity for what we're talking about. We're not going to get too deep into convergence of series or sequences at this stage. But right, you're hoping for a series solution to this equation. And namely, you're hoping to have this boundary value be correct. So let's just take f of x equals u 0x, and you kind of plug it in. And what is this going to look like? Yeah, so you just get b sub n times sine of n pi x over L. And of course you have this condition that 0 equals f of 0 equals f of L. I mean, the endpoints are always held fixed. So then you ask yourself the question, is it true that every function with these initial conditions can be represented with such a series? And series representation of functions shouldn't be like completely alien to you, because like if you look at the following collection of functions. And I'm going to use a linear algebra term. I'm going to look at the span. So, which is like equal to sort of like the collection of power series, right? Where these coefficients C1 can be kind of arbitrary. And one of these questions that you ask yourself in calculus is it true that a general function can be written in this way? And so you quickly learn that if it's true, then the following formula must hold good. Like it must be true that you're looking at like the nth derivative of f at the point 0 divided by, again, factorial times x to the n. So you find in your calculus class a formula for those coefficients. If it's true that this formula holds, then those must be the coefficients. You also may learn in calculus that functions that have this decomposition or have a special name, they're called real analytic. In the large landscape of all functions out there, most are not real analytic. Most functions do not have a setup like this. In fact, most functions aren't even differentiable. And here we've got something different. So instead of using this sort of basis of functions or this independent set of functions, we want to look at a new set of independent functions, namely sine of pi x over L, sine of 2 pi x over L, so on and so forth. And you're asking yourself now, like, given this function, can I decompose it in terms of basis functions? Or more properly, you might ask, under what conditions on f is it always true that f has this representation? And then the next thing you ask is, how do I find the coefficients? Similar to the way I found coefficients for like Taylor series. So those are the two questions that are kind of on your mind. And yeah, here's the solution, or here's a method or an approach. So you've heard me talking like linear algebra, vector spaces, but with being non-specific. So let me be like a little bit more specific. Let me define V naught to be the collection of all functions from 0L to R with the property that you're 0 at the endpoints. And more than that, the integral of the square of your absolute value is finite. And I'll just write that as, I'll say it's less than infinity. It's my notation just for saying that integral is finite. Of course, you know that every continuous function will have finite integral, but I didn't put such a restriction. I just said arbitrary function, and there's lots of functions that aren't continuous. There's lots of functions that are defined everywhere that don't have finite integral, or like the integral doesn't exist for some other reason. You know, think of something like even just 1 over x and define it to be 0 at the point 0. It's a legitimate function. It's not in this space. But what I will say is that V naught is a vector space. And I won't verify like all 13 axioms, but certainly, let's see, if you take two functions, add them together, their endpoints stay fixed at 0. If you take two functions that are integrable and have finite integral, then by linearity of the integral, their sum will also, well, not exactly linearity of the integral, but it is true that their sum will also like have this property. So you've got a vector space, and you're now going to ask yourself, oh, and by the way, sine n pi x over L is certainly an element of this vector space for every n. So you're asking yourself now, like, is V naught equal to the span of all those like countable vectors? Or, I mean, not to get like too deep into the terminology or language there, but that is the question. And so how do we resolve questions like that? In linear algebra class, what we took advantage of was the inner product on the vector space. This vector space also has an inner product. And I'll show you what it is. There's an inner product on V naught. I'll remind you the definition of inner product, but first I'll get this out. Namely, the inner product of two functions, say f and g are in V naught. What's their inner product? I use this notation for inner product. It's like an analog of the dot product, but for these two vectors, like what's their inner product? Just take the integral from 0 to L, f times g dx. It's a fact from analysis this is not an analysis class, so I won't show it, but it's a fact from analysis that if you take two functions that have this property, then it will also be true that this integral will exist. And that'll be so well defined. And so what are properties that an inner product needs to satisfy? Like it needs to be true that you take an inner product with yourself, you have to be bigger than or equal to 0. And it needs to be true that if your inner product is 0, it needs to be true that your inner product with yourself is 0 if and only if f is equal to 0. This is basically true. I mean, it's possible to look at a function that you know, let's look at something like f of x equals 1 if x equals 0 and 0 else. Then unfortunately, integral of f squared dx will be equal to 0, and yet function f will not be. So that's a small caveat, but later on in your analysis class, you'll find a way to formally to get around that. But now, just for here, I'll tell you that if it's true that like the integral of f squared is equal to 0, well, you know, if f squared were continuous, then the function would be equal to 0. We've talked about that. If f squared was discontinuous, then at these points of discontinuity, you could have like examples like this where the function wasn't exactly 0, but there can't be too many points of discontinuity, and that will not end up affecting our arguments. So sort of maybe brushing over a little bit of detail there, but that's for analysis class. The other thing you need to be for a norm, you should be symmetric, which is definitely true, and you should be linear. Which is definitely true. It follows from linearity of the integral. And so what I want to do is I want to at least figure out some formula for what B sub n has to be. And I'm just going to straight up use linear algebra. So I want to take the inner product of f with sine m pi x over L. And why should I care about that? Well, let's sort of probe into this. So f is like a limit, so n goes to infinity, partial sums. And you can certainly pull the limit out of the inner product. Inner products have to be continuous. So this is basically always okay. And so you've got this partial sum. And I'll substitute in what that's equal to. So partial sum, and now you're taking what? Pull out the constant b sub n. So yeah, linear, and the other part of linearity is that you can pull out a constant, right? So constant times f inner product with g is equal to c times inner product f times g. So I can write this as the b sub n times sine pi n x over L inner product with sine pi mx over L. Which looks like it's not going to be helpful at all. Actually, before I go on, any questions or comments on what I've said? It looks like that might not be helpful at all, except let's actually take a moment and try to calculate this. So let's actually try to calculate pi nx over L sine pi mx over L. And so this is now integral from 0 to L of this product. And you may remember this from your integral calculus class. In fact, we're already kind of primed to do this from our knowledge of trig identities, because you can remember that there's this product to sum trig identity that says this is something like 1/2 of what? I wrote it down because I never really remember. So this is like, well, actually, what I'll do first is I'll make a substitution to kind of make this a little bit easier. So I'll take u substitution, u equals, you want to just do pi x over L. And so du equals pi over L times x. And if I rewrite this, this is now 0 to pi, right? X goes from 0 to L, so u goes from 0 to pi of sine of n times u times sine m times u du. And what's the constant? So dx is so du is pi over L times dx, and therefore dx is L over pi du. So I get L over pi. Okay, and so now this is like more cleanly written in that product to sum formula. So you divide by 1/2, and this time you get cosine n minus m times u. Is it minus or plus? And then I get minus cosine n plus m to du. And you can see that this is going to be 0 if n is not equal to m, because if these two things are different, then just take their antiderivatives, which will be in terms of sign, which in sign vanishes on the endpoints. So that's no problem. But if m is equal to n, then what do we get? So continuing.
Can you go back to sine squared?
Yeah. You could do it with sine squared. I'll just do it the way that it's here, just because I already got it written down. If you do it with n equals to m, then this term you'll integrate and get something in terms of sine, which will vanish just like before. This term is the number 1. So the integral just becomes integrate the number 1 du, which becomes L over 2. So the pi's drop out. So you end up with this. Well, you end up learning that these functions are an orthogonal set. Which is kind of nice. So these functions are orthogonal with respect to the L2 inner product because of the fact that this inner product is equal to 0 whenever I take two different ones. And if it's non-zero, you get this nice constant. So you could scale them by a constant to even get like an orthonormal set of functions inside that vector space V naught.
How did you get 1 as the exponent?
Because cosine 0 equals 1. And integrating this gives 0. Yep. So this is heavily dependent on the boundary values. Okay, cool. So maybe I can erase this first part. If you take this back up, I mean, you can see now what we're doing is just a linear algebra calculation. If you want to find out the coefficient that makes up a vector for this vector component, just take their inner product. And that's what we're doing. And yeah, there's a limit that I pulled outside to make it finite so I could use linearity. But if I do this now, I recognize that this is 0 unless n is equal to m. And so what I'm left with is the limit as n goes to infinity of, well, there's only one term here, right? So it's like bn, and then when these two are both equal to n, I get L over 2. So I get L over 2 b sub n. Well, they're equal. It doesn't really matter. Oh, I see. It's the way I've got it set up. The n was the dummy variable here. Yeah. Right. Yeah. Thank you. So no, because what you're doing is taking the limit of a constant. And now you've found a formula for b sub m. And it's valid for every single m. So what is that formula? It's 2 over L times this inner product, which I remind you is the integral from 0 to L of f of x times sine m pi x over L dx. You may or may not have seen it before, but this is the so-called Fourier sine coefficient of a function. Yeah. Well, since all of you have had linear algebra, we can put that perspective on it, which is quite nice. And so I think that this is kind of There are things to check, but I think they're checkable and it will work out. So we really only needed the condition that function f was inside v naught, which is like saying that you're square integrable on the interval and that you have those endpoints. And then it'll be nice to write down a formula. So then if u tx has a series solution, so if utx plus u is equal to this sum, then it'll be true that f of x is equal to b sub n times sine n pi x over L, with b sub n given by that formula, and it'll be true that utx is equal to the sum, if n goes from 1 to infinity, of well, vn times phi n, right? And so this was like, so I've got my constant b sub n, and I've got v sub n was like e to the minus n squared pi squared x, or pi squared t times L squared. Did I get that right? Times sine of n pi x over L. I'll check my own calculation and see if I agree with myself. Yeah, right. So to put the pieces together, you need this coefficient, you need this formula for the Fourier coefficient. You needed actual vector space upon which you can do the linear algebra. And then you say if it's true that this is valid, which in general it won't be. But for the functions that make this true, you know, what's going on?
This class is just so strange.
Yeah.
It's just really strange.
Well, a lot of the things are phrased in terms of like if-then statements, you know, because this field is just so difficult that you try to solve the equation any way that you can.
Does this only work if the endpoints are called the same as the curve?
Well, this works, so I've been very careful. So this works exactly as I've described, you know, but it'll have to be true that u is this sum. So if you knew that in advance, like we didn't conclude this, that's my point, we assumed it. And at least in the case of Taylor series, you know that if you're a Taylor series, you are real analytic, which puts a huge restriction on you. And saying that this is so also puts a restriction on you. But if this is true, then your initial condition will have that formula with the coefficient having this formula. And this will be your formula for u. And the good news is that at least it works for the sandbox of functions that we like to play with in calculus, you know, like polynomials, you know, or like e to the x, or you know, functions that are real analytic, you know. So that is kind of good and comforting, and you can start doing real examples. At least, like, I can now ask you things like homework or whatever. Say f is equal to x squared, you know, then like find this formula. But then all you have to do to solve it is find the Fourier coefficient. Oh yeah, so x squared times sine of x. You know, with the right scaling, you know, it's like x squared times sine of x on the interval from 0 to pi, or x squared times sine, you know, pi times n, pi times x over L or something.
That should still work if the points are the same, it's not zero. You just move the temperature scale, right?
Yeah, so I'll make your question a little bit more general. The question I'm hearing is like, can you use the same methodology if you have a different boundary condition other than this? And yeah, you totally can. And the problems that you get are called Sturm-Liouville equations. So that's coming next. But like in this case, these boundary conditions caused the cosines to drop out, and we were left with only sines. But generally speaking, like the more general question is like, can you write a function f in terms of both like sines and cosines? I got around that here by defining a very specific vector space in which to work with. But, that's something you could confront on your homework. Like you could just do like a derivative, like those Normand conditions or something. And then you could prove that the sine terms drop out and like you're left with cosines, because you end up with like an even function instead of an odd function or whatever. But this is the setup. And so this is the method of separation of variables as applied to the 1D wave equation on a rod. Okay, cool. Have a great day. And I'll see you later. Take care.